So having a powerful workstation is great, not only for Houdini but for working with any software. But what's even better is having a render farm. And of course this does not belong to me, and you might be wondering where I am in this noisy, slightly chilly room, and this is Aixponsa's server room. So the guys were so great to allow me to use their render farm for some tests on PDG to show me how that works when running it distributed. So this render farm consists out of 10 machines, each a dual CPU Xeon, and after I tinkered around with them a bit, there are only 9 usable PCs left, so let's not talk about this. So what my plan is here is I will install HQ Server on the top computer, controlling the remaining 8 PCs as HQ clients. And I'm going to show you how to use and abuse this massive distributed power in PDG, even for a single artist. But you don't need a full-blown render farm to be able to use PDG and distributed computing. Even if you have just a second computer, a laptop, a second workstation, basically anything where you can install an HQ, you can use this computer's powers to support you in Houdini. So let me just boot those up, and while they are booting, let me just mention the 2 most important points about working with a distributed computing. Basically, there are only these 2 things that you have to keep in mind. So on the one hand, and that's about the only things that you have to remember, and everything should be good. So let's get started.
Alright, jokes aside, let's install HQ on our render farm. And for that, what I have here in this environment is I've got a mounted network drive here, which is mounted as the same drive letter in each of my render nodes too. And I put here my current build of Houdini, which I'll install now on those nodes. For that, I'm going to use a remote desktop software, in this case RoyalTS, which was recommended by Aixponsa's CTO to me. And here I've got a list of my 9 machines sorted by their IPs. I will just remote desktop on the first machine here, which I will install the HQ server onto. So this is the machine, the virtual desktop, and I will just head over to the mounted folder on that shared network drive where I have my installer here, and I'll just copy that onto the desktop of this machine here. So now that that's been copied, let's just double click it and start the installation. This is just a warning that I assume comes from the fact that this node doesn't have a proper GPU installed, and that is due to the fact that it's configured for remote desktop work. So we'll just install anyways and just click through the standard values of my installation here. However, when it comes to choosing the components to install, what I want to do is I want to enable and check HQ Server for installation too. As for the destination folder, I'll leave this set at defaults as well, because what I want to do is on each of those individual nodes, I want to install Houdini into the same folder, having the same path for each installation. I don't want to uninstall my previous Houdini version, and also for my HQ server, I just want to stick to default values here. When it comes to creating a shared folder, I don't need to do that because I've already got a mounted drive here. So I click, I already have a shared folder. So, non-surprisingly, I've already installed a version of the license server, so I do not want to reinstall that. I'll just click the German word for no, called Nein. Alright, so the install has finished, and let me navigate to my main hard drive, where you can see that here a folder has been created called HQ Server, so let's dive into that. And in order to configure and set up my HQ server, I need to edit the hqserver.ini. And the crucial lines that I need to edit are these, pointing my HQ server installation to the shared folder on my mounted network drive. So I prepared another file here, which I'll just use as a cheat sheet. So my shared network host is the UNC path to the file server called aixserver02 in our case. So let's copy that over and paste it here. Next is the shared network path, so the path to the shared folder, also in UNC, let's paste that here. And finally, the mounted drive letter, so the drive letter that this shared folder is mounted to. And now we should be good to go, so let's save that. And in order for these changes to be effective, let's restart the HQ server. So let's close that and minimize this. And to restart this, we need to start the task manager, so I'll just right-click on the taskbar here and go to Task Manager, which is the same word in German as in English. Go to Display More Details, and then I've got the services up here. Again, German machines, German install. I sadly can't change that for now, but again, just go to the Task Manager and the Services tab. And then we're just going to sort this by name, scroll down a bit, and here's the HQ server. So let's right-click on that and hit Restart. So now the server restarted, and to check if that thing is running, I will locally on my machine start a browser and go to the address of that machine. So that's the address here. just added a colon with 5000 for the port. That's a standard port where my server is running on this IP address. So let's hit enter, and I can see I'm directly shown the HQ web interface. Also, this is the version that I just installed, so everything went smoothly so far. So let's minimize this again and head back into our remote desktop software and connect to the second node in here, where I'll just walk you through the installation of the HQ client. So again, same procedure. I'll open the shared folder, copy over the Houdini installer to the desktop, and I will just launch the installer. Again, the warning, we'll just confirm that with yes, and then just click through the default installation steps. Under components, we now want to choose to install the HQ client, leaving all the other defaults checked here. Again, default path for the Houdini install, same as on our server and the same as on our other clients. I don't want to uninstall the previous version, and for my HQ client, I'll also stick to defaults. The HQ server is not running on my local machine, but on the IP that I just input into my browser. It's this one here, so it's 192.168.1.161, like this. Port number is 5000, didn't change that. Again, let's leave this as default settings and it'll install. So we got an error message here that tells us that the Houdini setup failed to start the HQ client as a service. So let's try to manually restart this and just hit OK on that. Click Finish on the installation. And again, to restart a service, just right-click on your taskbar, go to Task Manager, and then into Services. Let's see if we have the HQ client. It's here. So let's right-click on that and go to Start. So that seems to run now. So right after that is running now, let's head to the actual install directory of the HQ client. So start our Explorer, head to our local drive, and we've got this folder called HQ Client now. So let's dive in there. And here we want to have a look at the hqnode.ini file. So let's right-click on that and say Open with Editor. And in here, that is looking fine. So I want to make sure that my server's IP address is set to my actual server. The port is set to 5000. That's the default for an HQ installation. And the shared network mount is set to my mounted folder's UNC path. That looks about right. So what I'm going to do now, and I will spare you this in the recording, is install the HQ client on my 7 other machines. Basically the exact same procedure as I did here. So while those installations run on all of my clients, let me just point out something rather important that caused me a bit of headache. So on my local machine, let me just head to a browser and open up a new tab. And in here, what you want to make sure is to have a certain tool installed on each of your machine of your farm, and it's called ImageMagick. And you can download it for free on imagemagick.org. It is a tool to actually do kind of scripted image processing, and PDG uses it a lot. This might change until final release, but currently what you have to do is install this manually in addition to your Houdini installation on each of your machines where you want to run PDG. So basically what you want to do is go to download up here and then download your binary for your system. In my case, I downloaded this Windows binary down here. And also when installing ImageMagick, make sure to check the toggle box to install FFmpeg as well, which is used in Houdini and PDG for tasks such as MP4 encoding. So basically make sure that both ImageMagick and FFmpeg are installed on all of your machines where you want to use PDG/tops. So now with our farm set up and HQ running, let's finally dive in Houdini and just build a quick example of what we can do with the farm. So what I want to build here is the classic volume advection setup, whose parameters I will then tweak using a few wedge stops. And as volume advection is kind of a computationally heavy thing, for outputting a few different variants, a few different permutations of this setup, I'll leverage my farm's power. So let's start building. Let's drop down a geosop here, call this one maybe advect_vol for advect volume, and then dive in there. Start off with a platonic, which I'll set to tetrahedron and just leave it at its default settings like this. Next I'll convert this into a VDB with the VDB from Polygon sub, and I'll just dial in a smaller voxel size of 0.0125 like this. So let's highlight that. And next let's build the advection setup. So what I want to do is first measure my volumes, curvature and gradient. So I'm going to drop down 2 VDB analysis nodes, wire in the VDB from polygons into both, and set one to calculate the gradient. Just set its output name to custom name and call this vel for velocity. And the gradient in this case is basically the normal direction of a volume. So the gradient is a vector perpendicular to the volume's surface. Let's set the second VDB analysis to measure the curvature of our volume. and just leave the rest as is. Now I'll attach a volume wrangle and use this to multiply the strength of my gradient that I just calculated by the strength of a curvature, thus yielding longer vectors where we have convex edges, like here at those edges. And maybe we'll also use this volume wrangle to mix in a bit of curl noise. Basically what I want to create in here is a vector field, which I'll then use to advect this volume here. So let's start with a few interface elements. Let's drop down a vector called namp for noise amp. And let's create a vector slider, a vector input field called noise_amp, like this. Create it. We can see we just created this. Let's set its values to 1, 1, and 1. Let's also create vectors. And let's just copy this expression for noise offset, call it NO, and noise frequency, call it NF. And create those interface elements as well. Let's set the frequency to 3 by 3 by 3. Let's copy this again, paste it down here, call it CAmp for curl noise amp, and let's call the interface curl_amp and create it. Set it to 1, 1, 1 as well. Copy these two, paste them down here, rename to CO/CF, and again, we'll be using those to drive the curl offset and curl frequency. Next, let's create two floats. One called max C for max curvature, so that's the maximum value coming in through this VDB analysis here. And we want to be able to dial that in manually, so let's create a slider for that, call it max_curvature. Let's copy this and do the same thing for a minimum. And we're going to use those float values to remap our curvature later. And that got a bit mixed up, so let's click on this cogwheel icon, go to Edit Parameter Interface, and let's move the max and min curvature down here, hit apply and accept. So let's set our curl frequency to be 4 times 4 times 4, and the maximum curvature to maybe 7 for now. Next, let's finally read the curvature value coming into the second input slot here. To do that, let's create a float value, call it C for curvature, and we'll just sample the volume coming in there. It's a float, so we'll just use the volume sample function, the second input slot, the first primitive coming in there, so the first volume, and at our current voxel position. Now, let's fit that. So what we want to do is fit the incoming value C, the curvature, which ranges between minimum C and maximum C, and we want to remap it into a range of 0 and 1. To be able to further tweak this, let's pipe this through a ramp slider, and create the interface for that as well. So here we can use this interface to remap the curvature. So let's set those endpoints to be a B-spline, and maybe add a point in here. Tweak that like that. To be able to dial in the overall magnitude of the effect, let's just multiply that with another value which we'll be able to dial in later, an overall amplitude, create that slider too, and for now set it to 1. Now let's add in our simplex noise, again multiplying our curvature value times the value of an X noise, that's a simplex noise function, and we will use these parameters up here to drive this function. So our current position times the noise frequency plus the noise offset times the noise amplitude, resulting in this short expression that lets us tweak the noise that will multiply in there. Next, let's create a curl noise, call this one curl, and we're going to use the curl X noise function, so a simplex curl, again, this time using these parameters to drive the appearance of the noise. Again, times CF for the frequency, plus CO for the offset, times CAmp for the amplitude. Finally, let's mix everything together, create a final output vector, call this one V, and let's just mix between our velocity coming in here, so that's the VDB analysis there, and our curl that we just created. And to drive that whole thing, let's create another float slider, call this one curl_mix. And all of this goes into a neat little function called lerp, which just mixes between those two values, depending on this third value. So 0 in this third value means use only this value, 1 in this value here means use only this value, and everything in between just mixes them. So let's create that final curl mix slider down here, and maybe set it to 0.5 for now. Back to our code. What we'll finally do is multiply our vector v times a vector that we create out of this value that we stored in C. We're just gonna create a vector out of this single float value, multiply our velocity v with it, just to drive its magnitude a bit. so to shape this volume into a bit more intricate appearance. Finally, let's write that out. V at vel equals V, like this. Let's keep our fingers crossed. Okay, no major typos. So let's maybe check on this appearance of this volume by dropping down a box, piping this into an ISO offset, attaching points from volume just to generate some points in space like this. Maybe increase the box's size a bit, and then drop down a volume trail here, piping the points into the left port and the velocity volume in the right port. And we can see, well, not that much, but we created some vector field generating these slight trails here. So if I change the parameters such as the amplitude or the curl mix, I can see I'm modifying this field here. So that's working. Okay, let's get rid of all this. This is just to visualize what we've done so far and maybe save this. And finally drop down a VDB advect wire in our incoming original VDB in the left slot and the velocity volume that we just created in the right slot and highlight it. And you can see there's already something happening on these edges a bit. What I want to do now is take all of this, what we just built, and drop it into a loop so that it's repeated over and over again. For that, let's just in here attach two nulls, one below the incoming VDB, call this one in, and let's drop down another null, and we'll call this one out, like this. Now the for loop, it's going to be a for loop with feedback. Let's just cut this in here, and our repeat begin goes in between the first null and the VDB from polygons, with the out going into the left slot of our repeat end. Let's just set the repeat end to one iteration for now and highlight it. So there's no change because all of this here has been run only once. But as soon as we begin to increase those iterations, we can see the advection gets further and further. So let's maybe run this for, say, 40 iterations, which takes a bit of time on this machine. As you can see down here, we're slowly cooking our passes, resulting in a shape like this. So that's what I expected, but as you could see, this took around 50 seconds on my machine, so it's quite a lot. At least if I wanted to crank out a few permutations of this. And also, this looks a bit too intricate at points, so what I could finally do is tweak that setup a bit. I will just disable the loop for now, so that we're not calculating this over and over again. And I just want to insert a VDB smooth SDF before the out null here, having it set to mean values, and maybe running this only 2 iterations. So after each cycle of that loop, the resulting advected volume gets a bit blurred out in order to prevent those overly strong fine details appearing in the whole advected volume. Okay, let's re-enable our loop, which has now the advantage that it's only running about 30 seconds, and also we're getting a bit less of this extremely fine detail. So that's my standard basic advection setup here. Finally, let's convert this back to polygons using the convert VDB set to polygons, and let's increase the adaptivity to 0.1, wire this in here and highlight it, and we can see we turn this into a polygonal mesh. Let's attach a null to this, call this one out underscore advected, and we're finally good to go to build our top setup. So my plan for now, just for this short demo of the farm, is to just have 2 wedges in there. And what I'd like to wedge is, on the one hand, in this volume wrangle, the max curvature value, and also the curl mix. So let's get up one level and drop down our top net, dive in there. And again, we are greeted by this local scheduler here. However, this time we are not running this locally, we are running it on HQ, on the farm. So let's exchange that with an HQ scheduler and just delete the local one. Okay, this one has several parameters that we need to take care of. First, we need to point it to a working directory. And as you can see, I already saved my file on that shared folder here. So my transfer, MSC, and then in the PDG directory. And that's exactly the working directory I'll point it to. And I will do this explicitly. So underscore transfer /MSC/PDG, like that. Next, the HQ server is anything but my local machine. It's the machine with the IP 192.168.1.161, like this. Port 5000 is still valid. The universal HFS points to the directory where Houdini is installed on all of my machines, and that's why I stuck to those default installation paths, so I can just exchange this with my default installation path that I also have on my local machine. Let's just quickly navigate there. So here we are, program file side effects, and this is the Houdini version I'm using. So let's just copy this one here and paste it in here and just exchange the backwards with /. like this. Also, finishing with a slash doesn't hurt. Finally, just to check, I can check override local shared root and go to load from HQ. So yeah, for Windows, which I'm working on, my local shared root is the Y drive, or the shared folder mounted to Y. That is looking good. So let's finally build our small topnet, consisting out of 2 wedges. Wedge 1, just copy and paste this. Wedge 2, a ROP geometry for caching our meshed volumes, and finally a ROP mantra to render our preview. And I'm going to use the ROP mantra here because the nodes on my farm don't have a proper GPU installed, so using OpenGL with them is not supported at the moment, so I'll just render using mantra set to a really low setting just to generate an output image. Let's set up our wedge 1. Let's, for this example, do 5 wedges, add a wedge attribute, call this one maybe curl blend, and let's have it in the range of 0 to 1. Second wedge, again let's use 5 individual wedge values, and let's create a wedge attribute, call it max curve, and let's range it between 0 and 10, like this. Let's take those 2 attributes and wire them up or link them up in our SOPs level. So again, back into our volume wrangle here. Let's link up the maximum curvature first, Alt and then max curve. Again, let's cancel cook in here and head back to the topnet. Copy the curl blend back into our SOPs, and this time adding the attribute here in the curl mix slider like this. Again, now this is trying to cook as I change the values here, so let's just go with it. And that's the result with the default values of 0 that I get here. Let's not worry too much about that yet, and go back into our topnet and set up the ROP geometry for caching out our geo and actually loading it back in. So let's select our SOP, which we want to cache out, and we want to use the out_advected and cache this. However, instead of the frame, what we want to use again is the wedge index. So let's use 2 backticks and our wedge index there. Just copy this one and paste it one more time, and again add a second dot like this for our file path. Save this. And finally configure our ROP mantra for rendering here. Let's just copy this hip name here and create a subfolder by just copying this, and in front just pasting it with another /. And in here, instead of the frame number, I just want to use the wedge index. And again, if you don't want to use this @ syntax, what you can do is in the wedges here, check export to environment in both. So now what we can do in the ROP mantra is, instead of the $F4, spell out dollar and then capital wedge index like this, just if you prefer to stay in HScript. Now for the rendering, let's set this to really low settings, just for a preview, a quick one, like this. And finally, I want to create a camera. Let's just position this accordingly, maybe like this, back into our topnet and the ROP mantra. Camera is already selected. Let's just override the camera resolution and set it to be 720p by default for now. All right, that's looking good. Let's save this for now, and back in our SOP level, let's take care of our read back node, so loading back in those caches for rendering. Let's just drop down a file and a null, which will wire into this file, calling this one out_readback, like this. To fix this file path here, I'll head back into SOPs, into my ROP geometry, where I set the output file path, right click on this, say copy parameter, go back to my SOPs here, and in the file, I will just pass a relative reference into the file path input here. That is resulting in an error because we haven't cached out anything so far. However, let's just highlight this one here, go up one level, and just for rendering purposes add an environment light in here, and I'll just point it to some HDR. Let's just save this. Okay, now let's try this out. And I deliberately set my wedge counts to be 5 by 5, so I'm only generating 25 permutations and variations here. Because what you want to do, as with everything that you send on a farm, is test it before you submit it. You know it from your renderings, you just send out something, go home, come back the next day, and most of the frames are black, have some error in it, or are just not rendered properly. So please make sure before you commit and before you send this to a farm, just run a small test case. Let's just do that, save this, and without regarding the ROP mantra, let's just hit Shift and V, so basically force this to cook on the ROP geometry node. So far that is looking good. You can see we have 7 jobs running here. Maybe there will be an 8th client kicking in soon. Maybe we can check on the HQ server. We can see our job is running here, so I click on the job ID and then again on this job ID, and I can see there are already a few permutations that succeeded. There are a few that are running on my clients. So the thing looks like it is working. Maybe let's have a look at our work folder. So that's this one here. And under Geo, if I sort it by date modified, I can see this is the geometry my jobs are generating. And now I notice I made a mistake here. I pasted my wedge index twice, so that was definitely unnecessary. However, it's also not a huge issue as this is running fine here. Okay, one job left. Come on, Nutcracker 3. Yeah. So what I can do now when I highlight this, I can switch in between those different permutations of that setup that I've just generated. And when I go to my Philo dialog, you can see when I middle mouse click on this one here, this gets resolved to exactly the path where we wrote out our Geo 2. Let's maybe render this back into our topnet. Again, let's save this, flag our ROP mantra as an output, and hit Shift and V. Yes, we change this. Yes, we want to save this. Again, let's have a look at the server. There is my mantra job running here. And yeah, it's running on the clients. So let's have a look at the output images. Again, in our work folder here, the render PDG volume advection 1 is where we are rendering to. Let's maybe take this one here and open it up. Yeah, so we have a very, very coarse preview rendering, but it works. Okay, our jobs have finished now. All fine, all dandy. So what I can do now before I head home and let this run on the farm overnight is just crank up these wedge counts here to really high values, or maybe add a few different wedges, controlling some other parameters of my volume wrangle that's used to generate those velocity volumes that advect the volume around. Let this run overnight, and then hopefully come back in the morning to a bunch of different previews that I can then use to make a decision about which parameter values I want to dial in for final rendering or for final creation. Alright, so far for the basic intro to setting up your farm to run PDG/tops on it. A few things I'd like to mention here. The neat thing about this technique is that for the first time that I could think of, now a farm, to me at least, is more accessible because it can be used for more things than just simply rendering out images. It can be now used for intricate geometry creation, for geometry processing, and for creating and calculating through setups that were simply too heavy to massively iterate on them before. And finally, although this whole setup procedure takes a bit of time first, once it is running, a farm is really a pretty thing. As with PDG, you can now just use it as an extension to your local Houdini. It just feels like your local Houdini installation, just X times faster or X times more powerful. And finally, a farm gets more efficient with heavier projects. So if a farm computer can spend more time on the actual calculation and less time on the distribution of data or something like that, that's where it can really shine. So the heavier your project, the more efficient distributed computing is. And speaking of heavier projects, that might be a topic for our next tutorial. See you then.